Hello, everyone. Let's start. The topic of particle acceleration is very, very wide. So I just stop on some things which I think are the most important ones. And I will mostly, at least I will try to stop on the physical questions, not on solving equations. Sometimes I'll do solve the equations, but they are really school type equations, so you can hopefully easily follow that. So here is the outline of my talk. And the story started 100-something years ago when Victor Hess discovered cosmic rays. At that time, it was already known that there is radioactivity. There are some radioactive isotopes in the, around us, in solids, better to say. And I think by this time was already even known radon as a gas, but which is heavy and still confined to the Earth. So the air is somewhat conductive. It's conductive because of ionization caused by, at that time, people thought that this ionization is caused by radioactivity. So the idea was to take the balloon flight, and if you go higher and higher from Earth, you will see less and less ionizing radiation. You will see less conductivity in the air. So Victor has performed just that and has seen something absolutely opposite. The higher you go, the more conductive air becomes. From that, it was an immediate conclusion that the ionizing particles are not coming from Earth, they are coming from the space, somehow. What is the origin of these particles is still kind of, I wouldn't say that nowadays it's a great mystery, but we are not sure in all the details, but in general, I think we understand the situation. So what's going on? A primary particle, you have already heard about it, a primary particle hits a nucleus somewhere up in the atmosphere. Then it breaks this nucleus apart, and secondary particles are also energetic. They break other nuclei, and you have a very broad cascade which reaches the ground. And at the ground, you put the detectors, and you see the high energy particles coming from above. So that way, you can first detect the cosmic rays, and second, you can measure the energy of cosmic rays, because the higher is the energy, the more secondaries you have. This is the picture of Pierre Auger Observatory, and you see how these detectors look like. They are huge tanks filled with water, and the high energy particles going into the water produces Cherenkov light. So this Cherenkov light is eventually detected, and this way you know that something is going on. By the way, you can see here a radio antenna. It's not for the data relay. It measures the radio waves created by this sharp front of ionizing radiation going through the atmosphere. So it's another channel of getting information about the air showers. And the cosmic ray spectrum, again, you have seen it many times. You have seen that it's composed of many different types of particles. In general, we see a power law. This power law has some structure in it. This structure is not well seen here, but there is a knee, there is second knee, there is an ankle region. If you multiply by e to the proper power, then you get it flatter, and then you see the details much better. So what you see here is this first knee region, second knee region, and then the spectrum goes down. Well, it goes down all the way here, actually. So most of the energy is here. The energy is less, and this is just multiplied by e to the 3 to get it to the right, more or less overall flat shape. So what about the knee? There was a question in the previous lecture. I think I can a little bit answer to that question. And the idea is there are many ways to explain these two knees, but the main idea, to which I tend to believe, is the following. you have protons. Protons are the lightest particles in the universe, the more abundant particles in the universe. So mostly you think you will accelerate protons. You have protons, and protons are accelerated due to some energy. This energy is exactly the location of the second E. Beyond that energy, you still accelerate protons, but you lose efficiency and the spectrum goes down, like that. Then you have helium. When you reach to this energy, helium is already fully ionized, so you have twice the charge of a proton. And twice the charge means that all the electromagnetic forces are multiplied by 2, and the maximum energy is also multiplied by 2. So you have another need for helium, which is slightly higher by a factor of 2. And then you have a big gap between helium and carbon. There are no abundant nucleus between helium and carbon. Helium is produced during the Big Bang. Carbon is produced during the star burning their hydrogen. And even if you produce some amount of material with atomic number less than 6 for carbon, then you very easily destroy it in nuclear reactions. So you cannot accumulate this material. You can accumulate nuclei which are carbon and heavier nuclei. And between helium and carbon, there is a gap in nucleus charge. And this gap, if you have good imagination, you see two humps, one and another. So one hump is hydrogen plus helium. Then you have a dip, because there are no nuclei between helium and carbon. And then you have carbon, you have silicon, all the way till iron. And iron has charge 26. It's already also fully ionized by this energy. And if you see this energy and this energy, their ratio is strikingly similar to 26. Well, this gives some credibility to the picture. And then you lose efficiency for all the nuclei. You go down, and then you see appearance of something else. It's hard to believe that you become more efficient in accelerating particles if you go to extremely high energies, so probably it's another type of sources. And yes, if you think how energetic particles move in the galaxy, they are deflected in the magnetic field. As Luigi just said us, they diffuse out of the galaxy on a time scale which is energy dependent, but till to some energy. After some energy, the particles are not confined in the galaxy. Even if you take iron nuclei, they just go straight through the galactic magnetic field. For protons, it becomes, it sets up, this effect sets up at 10 to 18 electron volts. So above 10 to 18 electron volts, you do not expect to see galactic sources all over the sky. If you would see galactic sources, they would be concentrated in the galactic plane or even in the direction of the galactic center. They are not. So these particles should be extragalactic. And summarizing this part out, you have this galactic component of the cosmic rays at about few times to 10 to the 18. You have transition from the galactic to extragalactic cosmic rays, and these are probably somewhat different story in terms of the acceleration mechanism. Nevertheless, the picture is good up to this point. The only problem with the measurement that unfortunately cosmic rays do not have labels on them. They are not labeled made in somewhere. So we know that they are somehow produced, but we have no idea where they are produced if we just measure the cosmic rays. What can we do? We can try to think what's going to happen if you produce very energetic particles. And again, Luigi said that we will have, definitely we will have high energy radiation. If you have energetic particles, there will be radiation accompanying that acceleration. So let's try to think of sources. The sources of high energy radiation are observed with a good precision, good enough to be identified. There are many plausible candidates of particle acceleration up to high energies. But again, just to squeeze it into a single lecture, I will stop on several, which are the most prominent ones. The first is, of course, supernova remnants. What is that? A supernova is an explosion of star. Star explodes at the very end of its life. The massive star explodes, and the material that was comprising the star is flying away at a speed of several thousand kilometers per hour. Per second. And then it hits, at some point, it hits the surrounding interstellar material and produces a shock wave. And this shock wave accelerates particles. How do we know? Just because we see energetic radiation from this. This image on the left is in X-rays. This image on the right is at TV energy. The difference in energy between these two is 9 orders of magnitude, and still you see almost the same. 9 orders of magnitude, just to get you an idea, is like between radio waves and optical. The surrounding, if you will be able to see in radio waves, the surrounding will be completely different than in optical. You will see something completely different. And here it's the same. So this is the spectrum. The spectrum, here on the picture you see the measurements, which are dots and things like that. And the curved lines, which are models. Models are not essential at this moment, but what you have to gain from this picture is that you see this is the flux of energy. E squared times number of photons per unit interval is the classical way of presenting the so-called spectral energy distribution. This graph immediately tells you where the energy is. And you see that most of the energy is in X-rays, but even at TV you have few percent of the energy. So it's a very, very broad spectrum. It's definitely non-thermal, and definitely to produce photons of TV energy you need at least particles of the same energy. In fact, significantly larger energy. Another one, just to see that they are all kind of the same. The spectra of all supernova remnants. This one was not unique. Now, pulsars. Pulsars are rotating neutron stars. Neutron stars are small. They are about 10 kilometers in size. And their magnetic field is very, very strong. It's 10 to 13 Gauss or something like that. If you rotate very quickly a magnetic dipole with this magnetic field, what you expect that at some distance from the surface, the field lines, imagine that the magnetic field lines are something which you can feel. It's not something imaginary. I will tell you why. Because at the surface of the star is rotating at a fair fraction, by the way, of the speed of light. The surface of the star, of the neutron star is rotating. And if you have a magnetic field line without electric field line, then how conductive matter on the surface of the star would go through the magnetic field lines at this speed? No way. What do you have to do? You have to introduce an electric field. This electric field is generated by electrons and positrons, which are drawn from the surface and put somewhere in the magnetosphere. And this electric field lines gives you the E cross B velocity, which is just equal to the rotational velocity. And the whole magnetosphere is rotating as more or less a rigid body. So if you go further away, the speed of rotation increases. At some point, you reach the light cylinder, where the speed of rotation should be equal to the speed of light. No way you can keep charged particles there. What you do, what you see from this, the charged particles are just thrown away at approximately the speed of light, at very high speed, and they also carry some electromagnetic energy with them, of course. So this creates a pulsar wind. And this pulsar wind is more or less in the equatorial plane of the pulsar. Something goes along the rotation axis, but most of the energy goes in the equatorial plane. And again, you see these particles hitting the surrounding and producing a shock wave, which shines in X-rays, and not only. The spectrum, again, extends to very high energies. And this is another very beautiful spectrum. The Crab Nebula is the best example for everyone. If you build a cosmic ray detector, if you build a cosmic detector of gamma rays, X-rays, or whatever, first what you want to do, and first what is actually done, is that you point it to the Crab Nebula and see what you see. This is actually the way that you cross-calibrate different instruments. You see the Crab Nebula, which is very well observed at different energies, and you can cross-calibrate using this nature-made standard. And once again, you see the spectrum extends to an extreme. Again, you produce very many X-ray particles. Now, coming outside of the galaxy. This is Centaurus A. This is one of the representatives of the so-called active galactic nuclei. And this is the nearest active galactic nuclei, but in fact, it's kind of a toy blazer. Its energy output is very much smaller than for a typical blazer. It's well known just because it's very close. Anyway, what you see here, this is the galaxy. Actually, these are the dust rings of the galaxy, the dust plane of the galaxy. I don't know how to call it. And these are two jets which are emanating probably in the direction coincident of the rotational axis of the central black hole. In the center, we believe there is a supermassive black hole that is accreting matter. And this accreted matter, as it goes closer to the black hole, some amount of this matter is thrown away, again at approximately speed of light. Elena Nokhrina has just told us, not just a couple of days ago, that active galactic nuclei produce jets which have visible superluminal motion, and that means they are not just fast, they are ultra-relativistic. They have bulk Lorentz factor, which is tens or maybe even up to 100. Another example, this is more typical, active galactic nucleus. And here you see the very powerful jets, and you can barely see the galaxy. The galaxy is nothing compared to the jets. And the scheme, you also have seen it in different talks. The typical scheme, unification scheme of active galactic nucleus, is that you have a supermassive black hole surrounded by a accretion disk, and then it's surrounded by a torus of dust or some absorbing material, and then it produces in the direction normal to the disk plane, along the rotational axis of the central black hole, you produce a relativistic jet. And then depending on the viewing direction, you will see seemingly different phenomena, which are actually all the same. If you see from this side, you see a blazer, because the jet is shining towards you and it overshines everything. If you see from this side, you see an active galactic nucleus, you see the emission from the accretion disk. If you see from this side, you don't see the central part of this machinery, and you only see the lobes or something like that. The spectrum. This again, the famous blazer that produced, I think, 2 neutrinos, 3. I'm not sure, but this is probably the record-holding producer of neutrinos. And the spectrum has typical for blazars shape, which consists of 2 peaks, one at low energies. Here it's at optical energy, and another one at high energy. This is the representative of so-called GeV blazars, where the second peak is at approximately GeV. You have 9-10 orders of magnitude in energy, where the spectrum essentially doesn't change. I mean, the spectrum itself does change, but you have almost the same amount of energy here and here, and they are separated by 9 orders of magnitude. And finally, coming to probably the most mysterious phenomena in the sky, gamma ray bursts. They are now, well, first of all, gamma ray bursts are coming in 2 varieties. The long ones, which are canonical gamma ray bursts, and the short ones, which are less energetic, less frequent, and actually less understood. So I will stop on the long ones, These are canonical gamma ray bursts, as I told. And the long gamma ray bursts are believed to be a special kind of supernova when you have a core collapse in a massive star, but this massive star has to be devoid of its huge hydrogen atmosphere. So it should be a Wolf-Rayet star, a Wolf star that has thrown away all the hydrogen, and it's a bare helium or even carbon-oxygen core that is very compact. And when it starts to collapse, it produces a black hole in the center, and this black hole rotates very fast. And again, you have absolutely the same picture. You produce an accretion disk inside this collapsing star because all the matter cannot go immediately to the black hole because of the conservation of momentum. So you have to lose this momentum, and you lose it in the accretion disk. And then the material goes to the black hole. It rotates very fast at approximately the velocity of light. And again, you produce very powerful relativistic jets in the direction of rotational axis. And because the star is not very extended, it's a compact star, a relatively compact star, this energetic jet has some chance to bore through the star and go into a free space. And then you see a gamma ray burst if you are lucky enough to look along the direction of the jet, then you will see a gamma ray burst. This is quite complicated phenomenon, so let's move to a little bit later stage, which I will then at some point in my lecture discuss in more detail. And this is a really clean physical problem. So you have this material ejected at ultra relativistic velocity from the star as a jet, and then this material hits the external material. In this case, it's most likely it's just the stellar wind that was blowing from the star some time ago. And this material hits this interstellar material, the ejected material, and produces a shock wave. Now, this shock wave is very nice physical problem. You have one material hitting another material. You know the velocity of the material that hits the external material. You know the composition or whatever you need. The velocity is zero. The pressure is in this scale is also zero. So it's a very clean physical problem. You have a strong relativistic shock propagating into a space which is just filled with plasma, nothing else. No external radiation, nothing. So it's a very simple physical problem, a shock wave propagating through the material. Well, very simple, it doesn't mean that it's simple to solve, but it means it is simple to understand, and you don't have to worry about some details which are definitely around if you consider the gamma ray burst itself. When a jet propagates through the star, then you have interaction with the stellar material, all the things that complicate you. A problem that doesn't really allow you to understand the physics. If you want to understand the physics, you should take a simple problem as simple as possible. And this is the so-called afterglow of the gamma ray burst. This is the emission that extends. It's observed even days after the gamma ray burst. You can observe it. It's fading emission in X-rays. And unlike the gamma ray burst itself, which is erratic, the light curve is like that. This afterglow light curve is very smooth and very, very smooth. It's just declines as a power law, more or less. Then the spectrum. Actually, for a very long time, we were only able to observe this part of the spectrum, and occasionally there were appearing some, maybe a few times in the history, there were appearing some observations at sub-GeV energy. This emission is producing actually one peak. This was expected from theoretical reasons, that there should be another peak like in the blazars, but it was never seen until 2019, and then there was first detection that yes, there is a second peak, and you see the same structure as in blazars, a lower energy peak and the high energy peak. And again, the separation in frequency, the separation between them is 8, 9 orders of magnitude. So it's something is going on. You not just accelerate the particles, you accelerate them over the large interval of energies. So there should be some mechanism that does this. And the mechanism was produced by Fermi long ago. The figure is from 2012, but the Fermi, of course, introduced this mechanism much, much earlier. The idea was to explain cosmic rays even before people started to think about supernova explosions. The Fermi was thinking in the following way. At that time, it was already known, of course, that there are some clouds in the interstellar space, molecular clouds. They are magnetized somehow, definitely. The magnetic fields are ubiquitous. So what Fermi thought is that imagine you have a cosmic ray and you have a magnetic cloud. It hits the magnetic clouds and reflects. If these clouds are moving at random velocities, more or less isotropically distributed, then you can average these interactions over the angles and see what's going to be the average energy gain of a particle. And this average energy gain, this was the expression by Fermi because he thought of clouds that are moving at not relativistic velocities, and this is non-relativistic limit, and you see that on average, every collision gives you an energy gain which is proportional to the square of velocity. Hence, this mechanism was later called second-order Fermi mechanism.
So why it's always a gain, not a lose? It's random motion.
Yes.
Random collision, right? It's always a gaining energy rather than losing energy.
Well, in relativistic limit, it's because of two factors. In non-relativistic limit, it's just because you have particles which are coming from behind. They have less frequent collisions. They have to go behind, they have to catch up with the cloud. So the velocity difference is velocity of the particle, which is c minus velocity of the cloud. If a particle goes head-on, then it's velocity of the particle c plus velocity of the cloud. So you have more frequent collisions from the direction of velocity. And then if you average over whole directions, then this gives you a second-order term. But if you go to the relativistic limit, then if you have a cloud moving at relativistic velocity, then on average, every particle here in the background, every cosmic ray, would gain a Lorentz factor boost by gamma. But yeah, in the non-relativistic limit, you don't have it. And then what you can do with that? Imagine that particles can do many cycles of interactions like that. If there is no escape, if particles are just staying in the place where they are accelerated, they would gain energy infinitely in this approximation. But in fact, what you will see is that particles are gaining energy in one interaction, but they also have some probability of escaping this interaction region. And then in a very general way, you say that at every cycle, a particle gains on average factor of g, factor of energy gain, and in every cycle it has a probability of escape, which is p escape here. And if you have many cycles, then your energy is multiplied by g to the power of I is the number of cycles, and your probability of staying in the region, again, is 1 minus p to the power of I. Then you express I from this expression, and from this expression, is because it's the same I, you get the relation between the energy of a particle and the number of particles that are still being there. And this gives you the spectrum. In fact, it's not a spectrum, it's an integral of a spectrum. It's the number of particles at energies above some energy. So it's an integral from E to infinity. And then you can easily check that if your probability of escape and energy gain is are just numbers, not energy dependent, then a simple solution to that equation is a power law, and the power law index is here. Then, of course, you can ask how can you be sure that the probabilities do not change with energy? How can you be sure that the energy gain does not change with energy? And of course they do. But surprisingly, this picture works really well. So yes, we understand that there should be deviations, but these deviations are, well, let's put it in these words. These deviations are spread over such large difference in energy so that the overall spectrum still looks very much as a single power law. Not exactly, but I will come to that at the end of the lecture. By the way, I have to say something here. This is the second order Fermi acceleration. Imagine that you have two clouds, two big clouds, which are just approaching one another, and in between the clouds you have a particle that scatters that. And then you always have head-on collisions, and you don't have to average over all the directions. And you have an energy gain which is proportional to the first power of the velocity of these clouds, and this is called the first order Fermi acceleration. How can you do that in reality? You have a shock. In a shock, you know that the material is coming to the shock, and its velocity suddenly becomes smaller. So in a certain frame, you will see that there is material coming to the shock, the upstream, and there is material that is going in a different direction, the downstream. In the shock frame, they all go in the same direction because of conservation of mass. But in some frame, you will see them going in different direction, one towards another. This is just change in frame. And this is similar to two big clouds which are approaching each other. So it should be first order Fermi acceleration. Of course, to do some numerical analysis, you need first to solve the equations that describe the shock itself. And these are, I'm not going to do that, but these are three equations: number flux conservation, momentum flux conservation, and energy flux conservation. And you know, here you see that I put the relativistic equations. That means you have gammas. Gamma is the Lorentz factor. Beta is V over C, as usual in relativistic theory. And you have four numbers that are unknown: the density in the downstream, the pressure in the downstream, the enthalpy in the downstream, and the velocity in the downstream. For four quantities, you have three equations, and that's definitely not enough. To solve the equations, you also have to introduce one more equation of state that relates pressure to the enthalpy. If you do that, you solve the equations.
Yes. Sorry, may I ask you, if these quantities correspond to a shock or to a particles related?
Which quantities? The gamma and beta are hydrodynamic quantities.
Yeah, these three equations and the number density and so on. So what are these?
That's a good question. What's the number density? Yeah, you know, I put here the relativistic equation. So what's the number density in the relativistic equations? In a non-relativistic equation, it's simple. You know, you have some amount of some number of atoms in the upstream, and you will have the same number of atoms in the downstream. In the relativistic shock, it does not need to be the same. The shock could be, in principle, fast enough to break up not just the atoms, it can break up even the nuclei. It can produce positrons and electrons, multiplying the number of particles by a huge number. So what you do, you take some conserved number. For example, the baryon number density or the lepton number density, some number which is conserved exactly. So this is it. And you can solve these equations. Usually what you do in university, you forget about gammas. You put gamma 1 equal to gamma 2 equal to unity. You forget about them and you solve the equations, and this is called Rankine-Hukonian jump conditions, which are, I think, should be known to everyone in this auditory from the hydrodynamic courses. If you go to relativistic analog of these jump conditions, then you have tau jump conditions, and it's really a tedious work to derive them in a general case. But what you usually do in astrophysics, you don't solve the general case, you only solve two limiting cases. Well, in both cases, you always think of a strong shock. Strong means that you neglect the pressure in the upstream. It's zero. You only take into account the number density and the mass density in the upstream. Then it's enough to solve the non-relativistic equations to the extent that we need. The extent is what we will need later is the ratio of the upstream velocity to the downstream velocity, and this ratio actually depends on the equation of state. Oh, this is it. If your equation of state is non-relativistic, so that the pressure is 2/3 of the internal energy density, then the compression ratio of the strong shock is 4. If it's relativistic, when you have pressure which is 1/3 of the energy density, then the compression ratio is 7. And if you are in between, then the compression ratio is between 4 and 7. Ultra-relativistic shock is a different story. There you always have the upstream velocity, which is essentially c, and the downstream velocity, which is 1/3 of c. And the equation of state is always relativistic just because the shock itself is relativistic. Every particle is starting to move relativistically behind the shock in the downstream, everything. So equation of state is always relativistic. And if you solve it in a relativistic case, you get 1/3 of the speed of light. Now, how the things are going on. You have particles, well, the flow goes from here in the shock frame. The shock itself goes this way. The flow through the shock in the shock frame goes the other way around from here. Then the velocity drops down, and then you have downstream. And the particles which are accelerated are moving between the downstream and the upstream regions. And since from the point of view of this wandering particle, the downstream and the upstream are convergent, you will expect that the particle will gain energy. But you also will lose these particles continuously. If some particles, if particles go far enough in the downstream, they are lost. They cannot go the other way around and get back to the shock because the flow just tries to move them from the shock, and they go to the shock diffusively. So you know the diffusion time is proportional to the square of the distance, and if you're far away, you have too long diffusion time. That's it. The particle is lost. Now, the derivation that you always see in the textbooks, you can do it yourself in the internet. The derivation is like that. You try to calculate the energy gain for one crossing, and you try to calculate the escape probability, and then in the same way as I introduced you talking about the leaky box model, you calculate the spectral index. This is the typical derivation. I am going to show you something different, a derivation that doesn't consider particles alone. Let's try to think of accelerated particles as a fluid. So what you have? Oh, first of all, the accelerated particles are distributed like that. They have almost constant density in the downstream, and they diffusively go to the upstream, but the upstream always takes this particle back to the shock. So this is kind of exponential tail extending into the upstream. And if you have this exponential tail, these high energy particles, they have pressure. If their density is going down, then it means that there is pressure gradient acting against the velocity of the incoming flow. Or the other way around, the incoming flow does some work against this pressure. You just calculate that. So the power of acceleration, by definition, is the number of particles. This is an E, the distribution function, times differential of energy, times the typical scale that the particles occupy. And you multiply it by E dot, and this is the energy gain rate for all particles in this volume. And then you calculate the work of the flow against the pressure of these accelerated particles. And this is just delta P. P here is the pressure. Why delta P? Because if you think, and this is our assumption here, that the velocities, the upstream and downstream velocity, the velocity difference is constant at every point in the flow, then you have to integrate pressure gradient times this difference of velocities. Difference of velocities are constant, and then you integrate pressure gradient. You just have delta P, and delta P is outside. You have P equals 0, so delta P is just P at the position of the shock. So you do this. You take power balance, so the energy that goes to the particle acceleration is equal to the work that is done by shock, and from that you get the acceleration rate. And you see this acceleration rate is proportional to the velocity of the shock, as you would expect in the first order acceleration, and it's divided by the size that these particles occupy. And this actually introduces you some funny change, because this size, you can estimate it from different reasons, but typical estimate is that you have bomb diffusion. Bomb diffusion means that the mean free path of a particle is assumed to be equal to its gyro radius. So it goes, scales with energy, linearly with energy, and it scales inversely proportional to the magnetic field. So the mean free path of a particle is its energy divided by the magnetic field times some dimensional coefficients. So if you put, instead of L, if you put the solution of the diffusion equation, that gives you an exponent, as I told you, you put it there, and then you get, instead of L, you get the diffusion coefficient here, and the velocity of the upstream in the nominator. And the diffusion coefficient, if you put the bomb diffusion, then the end result would be square of the shock velocity times the magnetic field. So the whole acceleration looks like it's the magnetic field that is accelerating particles. It looks like that. Of course, what is accelerating particles is the electric field, but it looks like the magnetic field is accelerating the particles at some efficiency, and this efficiency is proportional to the square of the shock velocity. Although it's a first order acceleration, the energy gain is proportional to the square of velocity. Why? Because the smaller is the shock velocity, the longer it takes to complete one cycle of acceleration. And the time scale for one cycle is given by this L, and this L is inversely proportional to the velocity. So in the end, you have square of the velocity, not the first power.
Excuse me. Yes, excuse me. But here you were talking about the rate.
Yes.
So the rate is proportional to the square, and previously you were talking about the energy gain. So it's about the same thing.
Yes, but because it's a typical question, that the energy gain is proportional to the velocity, but the rate is proportional to the velocity squared. Yes,
So
it's a typical question. Why it's first order acceleration and you see the second power of velocity?
So that equation, if I am getting wrong or right, is telling us that it defines the time needed to be accelerated. About this exponential flow, right? For
The equation, you mean these equations or which
on the
equations?
previous slide, this is the last one.
Yes?
This defines the time needed to be accelerated.
Indirectly, the time is here.
Yes.
Yeah. Yes.
I mean, if
Exactly.
you solve this equation, you get an exponential.
Yes. That's it. And then you don't have to stop here. You can proceed in the same way. You take the divergence of the particle energy density of the particle density in energy space, and you equate it to the sink term of particles. The sink term is that the particles are being advected by the downstream at the velocity of the downstream. So it's just the number density of particles times the velocity of the downstream. The divergence term is somewhat more complicated, but you know, all the particles are moving in the energy space, and you just take the flux in the energy space, the velocity in the energy space, E dot, times the energy times the particle number density, and this gives you the flux in the energy space. So d over dE of that is the divergence in the energy space, and this is equal to the sinc term. Again, you write a simple equation, and if all the velocities are constant, I'm always pointing out that if all the velocities are constant, then the solution to this equation is a power law, and this is what you expect. And you can calculate this power law. You divide by the downstream velocity, and you get the compression ratio +2 in the numerator and compression ratio -2 in the denominator. That means you always get a power law, but the power law index depends on the compression ratio. And if you have a strong non-relativistic shock, then this power law index is this famous number e to the -2. Why this is so, I would say, peculiar? Because e to the -2 is the spectrum that is exactly on the verge of being integrable. In physics, we say this is physically integrable. Physically integrable, if you have a logarithmic divergence, it's physically integrable. Why? Because nothing in physics goes to infinity, and logarithm of large number, everyone is told something different. I was told that logarithm of large number is 20. Sometimes you hear that the logarithm of large number is 10 or even 30, but you know, it's all the same, essentially. So logarithmic divergence is nothing, and that means that the energy is equally distributed over all the domains up to the maximum energy that we will try to figure out. And before we go to this maximum energy estimates, just to show you another example of a setup where you can accelerate particles, it's also first of the Fermi acceleration. It gives you approximately the same result. This is acceleration in shear flows. Shear flow is the flow where there is velocity gradient in the direction perpendicular to the velocity itself. So the flow is from down to up, and the gradient is from right to the left. So, and imagine a particle that moves across these flow lines. Here, it is scattered in say, by clouds with this velocity. It goes to here, and it sees a cloud with different velocity. It goes backwards and sees a cloud with different velocity. On average, it's the same Fermi acceleration. How can we estimate the energy gain rate? Knowing all that I have said previously. Well, it's relatively simple. We know that it's proportional to the square of the velocity. So what's the square of the velocity? The square of the velocity is the velocity difference over the mean free path of a particle. So here is exactly this. This is gradient of velocity times the mean free path of particle, and the acceleration rate is proportional to the square of that. If you plug in the Larmor radius of a particle to go for bomb approximation, let's assume that it's bomb diffusion again, then you get that the acceleration rate is proportional to the square of the particle's energy. Once again, in the shock, it was independent of energy. Remember that? Here, yeah. The energy gain does not depend on energy. It depends on the magnetic field, but does not depend on energy in the shock. In this situation, it's different. It depends on the magnetic field in the same way. It's proportional to the magnetic field strength, but it also is proportional to the square of the particle's energy. And that means if you want to start particle acceleration, you will move slowly, very, very slowly, extremely slowly. You cannot do that, essentially. So it's not a standalone particle acceleration mechanism. I would say it's a particle energy boost mechanism. You can boost energy for particles that were pre-accelerated in some other way. Then it works. But if you want to start just from thermal particles, it's almost hopeless. What can limit acceleration of particles? We can proceed with this way up to infinite energy as it sees, but of course, first of all, we can lose the particles altogether. Altogether means what? The usual estimate is that imagine there is some large-scale magnetic field in the region of acceleration, and if particles' gyro radius is larger than this size of the accelerating region, then the particle just escapes. It has no chance to get back. And this is called Hill's criterion, and I'm always saying that this criterion was proposed by Cronin, and Hill just made it popular. Actually, it's Cronin criterion, but it's very simplistic and it doesn't give you the real estimate. The real estimate would be, what if the particles do not just leave the accelerating regions, they can diffuse out, and they will diffuse out. So let's take the acceleration rate and the escape time due to diffusion. And then you multiply the acceleration rate by the escape time, and you assume bomb diffusion. When I'm saying that you assume bomb diffusion, it doesn't mean that I cannot do anything else. I can, in principle. The way why I am taking this seemingly very simplistic assumption is because all that we see in the laboratory is consistent with bomb diffusion. If you try to build a thermonuclear reaction, a thermonuclear reactor, then you want to suppress plasma diffusion as much as possible, and all what they can do with the whole staff of thousands of engineers is they suppress it by a factor of 10. Not too much. And this is, again, in intentionally made laboratory device. So bomb diffusion seems to be a very good approximation for something realistic. So I take the bomb diffusion, I estimate the escape time due to this just normal diffusion. I take the acceleration rate that we calculated previously, and if you multiply the two, you get equation for E max, you plug it into here, and then you get an expression which is very similar to the Hill's criterion, except that you have an additional factor, which is square root of eta. Eta is the acceleration efficiency, and once again, in shocks, you have eta, which is proportional to the square of the shock velocity divided by the square of the speed of light. So the square root is just the velocity of the typical velocity of the accelerating agent, so to say. And in principle, if you have non-relativistic motions, then this number could be significantly smaller than the Hill's criterion, orders of magnitude, 2 or 3 orders easily. Now, I'm going to show you a picture of Tycho supernova remnant, and the orange and the yellow color here is the lower energy X-rays, and the bluish color is the higher energy X-rays. What you see here is something that is not consistent with the idea that the particles, the accelerated particles, are just escaping. Well, first of all, what is radiating there? Of course, electrons. This question was already asked in one of the lectures, and yes, electrons are radiating much more easily because they're easier to accelerate, and the radiation, the power of radiation, is proportional to the square of the derivative of the second derivative of the radius. So it's proportional to the square of acceleration, and that means that the light particles are much more efficient than accelerating. So everything is produced by electrons here in this image, the X-rays. Why is the bluish line? It's indeed like a line encircling the supernova remnant. Why it's so confined? Why it doesn't extend out or inside, as you would expect in the diffusion? Because it's not the diffusion that limits acceleration of electrons, at least not in this case. It's the radiation. Electrons are radiated at the shock, and you clearly see the shock here, and they lose their energy almost immediately in the place where they are accelerated. And in the loss-limited situation, it's completely different. So let's take the synchrotron power per unit particle. This is proportional to the square of the, this is the Lorentz factor of electrons, so it's a square of electrons' energy, and this is proportional to b squared. Then we have to relate this radiated power to the energy gain, and the energy gain is proportional to B. This is something, if you relate the two, this is something that depends on B, but more importantly, the energy gain does not depend on energy. So you increase the energy, you increase the losses, but you don't increase your energy gain. At some point, you just stop accelerating. And if you equate the energy losses and the energy gain, then you get the equation for the maximum Lorentz factor, and you see that the maximum Lorentz factor is inversely proportional to B, and if you plug this maximum Lorentz factor into the equation for the typical synchrotron energy, the B cancels out. And it turns out that the maximum energy of synchrotron photons produced by accelerated electrons does not depend on the magnetic field. And this is great because this is the greatest uncertainty in all the theories. We don't know what exactly is the magnetic field in supernova remnants or anywhere. There are simple no ways to measure the magnetic field. We can measure from satellites around the Earth, somewhere in the solar system, but that's it. The other measurements are very indirect. Well, if you are not speaking about Zeeman splitting or things like that, but this is not definitely applicable to these non-thermal situations. So the maximum energy of radiated synchronous photons is proportional to the efficiency of acceleration. And if we have a spectrum which is produced by accelerated electrons, then it gives you a way to estimate the efficiency of acceleration. And if you estimate the efficiency of acceleration, then you can estimate the velocity of the agent that is accelerating particles. Let's do this exercise. Again, the same spectrum that I have shown you. This is real astrophysics. We have gaps in the spectrum. Apart from the very important gap in the MEV range that Lily was saying us about, we have also a gap, very unfortunate gap, here in the soft X-rays. This gap is kind of unavoidable because the interstellar space is not transparent to very soft X-rays. It's not transparent to hard ultraviolet as well, because this quanta easily ionize the constituents of the interstellar material, and this way they are very easily absorbed. Anyway, we can try to draw a line through these points and these points. Someone does it kindly for me. Someone means a group of authors, and you can see many things like that. So you can estimate that the cutoff in the synchrotron spectrum, and this is the synchrotron part, the cutoff in the synchrotron spectrum is around 1 keV, and this gives you an estimate for the acceleration efficiency, 10 to the minus 5 approximately, and then it gives you the estimate for the shock velocity, which is 1,000 kilometers per second. Fortunately for the supernova remnants, this is historical supernova remnant. Tycho has observed the supernova remnant. We know exactly when it happened. We know its angular size. Unfortunately, we barely know the distance to that supernova remnant, but approximately we know. And then from that, you can just calculate the average velocity over this interval of time, and it's slightly larger, a few times larger. So it's a great precision. You can easily do a big science with just measuring spectrum. Another example, take the Crab Nebula. Could you tell me, probably you cannot, can you see the figures here? Oh, where is the cutoff in the Crab Nebula? At what approximate energy? Can you see? Yeah, it's somewhere here. Actually, it's written here, but I was expecting that you're fair students and you wouldn't cheat. Oh, it's somewhere here. You see that the spectrum goes like a power law up to some point, and then there is a gap, and then the other points are very much below. So the cutoff should be somewhere here, and the cutoff is at approximately 50 MeV, and this is actually the maximum possible energy that we derive for the synchrotron radiation. If the acceleration efficiency is unity, you cannot go past beyond unity because that would require that the accelerating force is larger than E times B, which is accelerating force is the electric field, right? So this would require that the electric field is larger than the magnetic field. It's hard to achieve in a non-human-made situations. I would say it's almost impossible to achieve. So it's the largest acceleration rate that you can imagine, and it's there. What does it mean? That the shock velocity is about c. It's a relativistic shock with the velocity close to the speed of light. As is expected, actually, because I told you that what you should see from a pulsar is an expelled outer magnetosphere, which is expelled at roughly the velocity of light. In fact, it slightly, well, not slightly, in velocity it slightly accelerates beyond that. In the Lorentz factor, it accelerates significantly. It starts from the Lorentz factor of about a few, and it can go in different models up to 10 to the 6, the Lorentz factor, the bulk Lorentz factor. It's not a single particle, it's the whole wind is moving with 10 to the 6. Well, but I should say it's in some models, it's not at all certain. It's not measured with some models. Anyway, yeah, it seems to work. And here I should warn you that at some point later, I will come to that back and ask you what question you should ask me bearing in mind this picture. So I guess you wouldn't ask this question right now, but at some point you would be able to do that. Now,
speed of the shock is larger than c. If speed of the shock is larger than c.
Larger than c? No, not to that extent. But yes, I can offer probably in advance, I can offer some currency, local currency to the one who asks me this question in double amount. So you are warned, you can be prepared. Anyway, the very last slides of my today's lecture are about the reality. Well, so far, it was a nice picture of idealized situation. Of course, there is nothing ideal in reality, and in reality what you see is that the escaping particles, remember that the shock does work, that the incoming flow does work on the accelerated particles and accelerates them. But of course, it means that the accelerated particles are slowing down the flow. So what you see, in fact, is that the flow velocity gradually go down. And go down to the downstream velocity, and this extent is finite. That means if you have particles with small mean free path, they move in this region and they see much smaller velocity difference, they see much smaller compression ratio, and the power law index is dependent on the compression ratio. So the smaller is the compression ratio, the larger is the power law index. Larger means by modulus, that means the power law becomes steeper and steeper. So for low energy particles, the power law should be steep. For high energy particles, the power law should be harder. And in fact, if you draw this line towards infinity, it goes past beyond 4, and who can tell me why? Any ideas why the compression ratio is slightly larger than 4 in a realistic shock? Lecturers will help the students, no? With the questions? No idea. Well, it's because the acceleration efficiency of a shock is not that small. In fact, the post-shock pressure, say 10% of the post-shock pressure is due to the accelerated particles, and accelerated particles are relativistic particles. So the post-shock material is a mixture of non-relativistic plasma plus some amount of relativistic plasma, so its adiabatic index is somewhere in between, slightly shifted towards the relativistic value. So it's not going to the 7, but it can be easily something like 4.5. What does it mean in terms of a spectrum of accelerated particles? You have this huge thermal bump, And then from that thermal bump, you extend first at a steep power law, and then it goes shallower, and then it goes up. So this one is harder than e to the minus 2. This one is steeper than e to the minus 2. And, well, Luigi asked the question, what could be the difference between protons and helium? And I cannot really answer that question, but I can speculate. All you can do at this point is becoming really a speculation because of the trouble here. The trouble is that the finite width of a shock is determined by the thermal particles. And therefore, for the thermal particles, it's not really a shock, it's a smooth flow. The thermal particles do not feel the shock itself, they do not accelerate, they just get compressed, and that's it. Only the higher energy tail of the thermal distribution can go into the acceleration. This process is called injection. And if in numerical simulations, if you can tag the particles that really enter acceleration, and you can do that, you will see that the distribution of these particles is, it has lost its central part. So the central part is not going into acceleration, only the very, very tail. And this is really the very, very tail. But then, if you have completely ionized hydrogen and partially ionized helium, once one electron is staying there, then helium per unit charge would have significantly larger energy. That means the Larmor radius of helium, once ionized helium nuclei, would be 4 times larger than for hydrogen. And that means you start accelerating helium at slightly closer to that point. So it's not the very, very tail of the thermal distribution, but just the very tail. So it has some preference. And heavier nuclei have this preference even to a greater extent. And that's why if you go to high energies, you will see approximately as much iron as protons, because iron relatively easily goes into the acceleration process. So this was my last slide, and the message from this slide is the general message is that it's a simple, consistent picture if you describe a simplified scenario, but if you go into the details, there is a lot to study there, and I think that even for you there is job in this field, so you can contribute still. It's not complete. Thank you.
Thank you very much for the lecture. So, questions?
Thank you for the lecture. My question may be silly, but when you showed the cosmic ray spectrum with humps, with needs, and with an angle, you said that this angle is, it corresponds with iron, as I remember. Yeah, this angle corresponds with iron of iron, and as I remember from nuclear physics that until the Fermi 56 with atomic number 56, the binding energy per this atomic number increases, and after it decreases.
Exactly.
So yes, and,
exactly.
The nuclei with nuclei less than iron, they are likely to fuse, and the higher of iron they are likely to fuse. So maybe the origin of these energies or this acceleration things are also in the nuclear fusion and nuclear fission.
Oh. The situation is like that. First of all, you are absolutely right. Up to the iron, the binding energy per nucleon increases, and that means if you go inside a developing star, you produce heavier and heavier elements until you go to the iron. Beyond that, if you want to produce, you can produce heavy elements, but this is done at the expense of losing thermal energy, not generating it, and the star loses its stability and collapses. Only the core-collapsed supernova can produce heavy elements. In any case, this is exactly the reason why there is an iron peak in the abundances of the elements. Iron is much more abundant than any element in the neighboring part of the periodic table. But beyond iron, there are no abundant elements, really. So this is the reason why if you have a maximum energy that depends on the charge of the nucleus, it's proportional to the charge of the nucleus. If you have this maximum energy, then you have the smallest for hydrogen, 2 times larger for helium, 26 times larger for iron, and nothing beyond iron. Oh, I'm sure that there is even uranium in the cosmic rays, but it's going to be a really, really hard task to measure uranium in the cosmic rays. In fact, it was quite a big achievement that at the highest energy cosmic rays, they were able to distinguish between protons and iron. This was already a big achievement.
Okay, thank you.
Maybe some naive question. Can you show the slide with the equation of state and specific heat?
Next.
Maybe next, yes,
Yeah.
yes. And as I know, all this motion and this equation of state maybe can be used only if you have an equilibrium state. And it's
No.
and you can write it only in the assumption if that there are some characteristic volume where you could introduce the pressure, the temperature, and so on.
Mm-hmm.
In spite of here, you use the intensive thermodynamical parameters. But the question is, what is your characteristic average volumes in which this equations take place?
As you see, is it working? As you see, the people are smart here. They do not use temperature, so they do not imply that there is thermal equilibrium. You can do that, but it's not at all necessary. To write this equation, you only need the fact that the kinetic energy, is proportional to the square of the momentum. To write this equation, you only need the fact that the kinetic energy is proportional to the momentum to the first, so linearly proportional to the momentum. So this is the difference between relativistic and non-relativistic. And about the volume, yes, you are right, of course, that there should be some kind of minimal physical volume where it applies if particles have no chance to change the direction of their motion even through the collective interactions, through the magnetic field, and yes, there is no shock at all, and it's a completely different story. But if there is magnetic field, the volume is essentially the cube with the size of the Larmor radius, more or less. It's the minimum volume that you should consider. You cannot go beyond that. But in a typical situation, Larmor radius is much, much smaller than the size of the system. So you don't really worry about that in astrophysics.
Okay, so any other?
Thank you very much for the talk. I have a question about also the equations, and my question is about magnetic field. So we have dependence on the magnetic field, and I can assume that it's not homogeneous. And if it's not, then maybe the velocities will be changed. And then the question is, in which limits we can use the assumption that velocities are constant?
Yes, you are absolutely right. Well, the magnetic field is inhomogeneous in two respects. First, it's locally inhomogeneous, which means that the magnetic field is not uniform, it's kind of turbulent. But locally inhomogeneous is not that big a problem because scattering in the magnetic field is a statistical process. If you talk about diffusion, it's a statistical process. So the statistical process can still average over over the volume that we just discussed, over the volume of approximately few times the Larmor radius, and it works fine. But then, yes, of course, it's not the local magnetic field. At some point, it's some kind of an average magnetic field. But then there is a second complication possible, that even statistical properties need not to be the same in all the points. Closer to the shock, you may have larger scattering. Further from the shock, you may have smaller scattering. And this really can be a game changer, really. I hope that in the next lecture I will have time to show some extra slides to answer that question in a more proper way. But in few words, yes, it could be a game changer. Yes.
Thank you.
I kind of second the question of Sergey regarding the thermodynamics.
Mm-hmm.
So we know this famous Maxwell diamond
Yes.
example, which can selectively
Yes.
place high energy particles in one volume and low energy particles in another.
Yes.
So this Fermi mechanism is somewhat doing a similar thing,
No.
right?
No.
No?
Not at all. This is exactly why Fermi had power of 2, because there is no selection. It's just average. You just average. That's it. If you have selection, he would have the first power. Maybe I do not understand the question properly. I don't know.
We began with shock waves
Yes?
and low energy particles. In the end, we have
Yes.
shock waves and high energy particles.
In the
It's
end,
kind
we,
of
sorry, just to put it in a proper way, there is a tiny detail here, and you know that the devil is in details. The tiny detail is that you end up not with the shock and high energy particles. You end up with the shock and a tail of particles which extend from very low energy to the high energy. So what you do is instead of having a Maxwellian tail, you produce a power law tail. But the majority of particles are still thermal. And almost all the energy in particles is still in thermal particles. So it's a small contribution in terms of energetics, but in terms of radiation, it's absolutely dominant, because the more energy you have in a single particle, the easier you produce radiation. So in a radiation sense, the accelerated particles completely dominate the whole story. But in terms of dynamics, they are, no, it's just perturbation.
Thank you.
Thanks for the nice talk. I have a question regarding the assumption of the Bohm diffusion. So, I mean, to have the efficient acceleration, we need slow diffusion in principle, right? So, but the Bohm diffusion, of course, sometimes is regarded as a kind of lower limit of the, but it goes with energy very quickly as E to 1. So, I just wondering if we assume other type of diffusion, does it alter the estimation of, for example, your escape limited maximum energy, or its loss limited maximum energy?
Well, if you think of electrons, then probably acceleration in all interesting scenarios will be always limited by radiation. For protons, of course, it's not the case. But then, even for electrons, if you change the diffusion coefficient, what you can change is you can change the dependence on the energy. And that means you will produce a different power law. And yes, people are discussing different diffusion coefficients. For example, they consider turbulence, Kolmogorov-like turbulence or Kretschmann-like turbulence, and they all give you different coefficients. as far as I would see this problem, I don't think that we have enough observational data to get away from the bomb diffusion. Bomb diffusion seems to be natural and it gives you reasonable results, so to say. And by the way, the maximum energies are also, you may view it in a different way. The bomb diffusion, acceleration with bomb diffusion gives you maximum energy which is consistent with observations, but then you can just to turn it the other way around. If you see the observations, you see the maximum energy, you can try to calculate what's the diffusion coefficient. And that gives you that. And then, of course, you can speculate that at the maximum energy, the diffusion is bomb diffusion, but at lower energies, probably it's not bomb diffusion. And I don't know how you can, in principle, exclude that. Unless you can go and send satellite inside a supernova remnant just to measure the distribution of particles directly.
So, thank you for your talk. My question is related to the long and short gamma ray bursts. And what is the criteria of how we classify these long and short gamma ray bursts? And if, for example, it's 2 seconds, so how we classify signals that locates near these 2 seconds? And if I understood correctly, long and short gamma ray bursts corresponds to mechanism or their creation. And do you have any evidence of the existence of a third type of mechanism that corresponds to the signal that locates between long and short gamma ray bursts? Thank you.
The actual distinction between the long and short gamma ray bursts is in physics. And here the situation resembles what happened once in supernova field, when there was a clear distinction observationally between type 1 and type 2 supernova, and then it turned out that some of type 1 supernova are actually physically similar to type 2 supernova, and some are not. So now we call them not type 1 and type 2, we prefer to say co-collapsed and thermonuclear supernova, right? So I would say it's the same situation. You cannot really distinguish on the basis of duration. There are some bursts which look in other respects very similar to long bursts, and they formally can be classified as short because they are short duration. There are some bursts which are relatively long, but they fit, in other respects, they fit the description of a short gamma ray burst. What could be a quantitative, even I would say qualitative difference between them is presence of an afterglow. In long gamma ray bursts, you always see an afterglow. In short gamma ray bursts, you sometimes see an afterglow, but it's weaker, it's shorter, it behaves differently. And in many cases, you don't see it at all. This is the definition. And why? It's because long gamma ray bursts are exploding in an environment which is the stellar wind, which is close to the source itself, is relatively dense environment. And the short gamma ray burst, if we believe the current day's picture, this is the collision of 2 neutron stars, and it happens in almost empty space. So you don't really produce a strong external shock, and that way you don't produce a strong afterglow. So that way you can, in principle, kind of distinguish between them, but not on the basis of duration.
All right, so any other questions?
I'm sorry, maybe I missed your definition. V2 is the sound is speed of sound. No. In the same slide, which was.
I will show you. Where is it? I can't find it. Anyway, V1 is the V1 is velocity in the upstream. V2 is velocity in the downstream. 1 is for upstream. 2 is for the downstream, and it's easy to remember because the material comes first to the upstream and second to the downstream. As the flow goes, first in the upstream, second in the downstream.
Okay, So the last call for the questions. So if not, let's thank this lecturer again.